All right. Well, welcome everybody. Thank you for being here. Such a great turnout. My name is Niels. I'm one of the volunteers here. For those of you that are somewhat new to the shop, and I see new faces, so that's great. This shop is obviously a second-hand bookshop. You must have noticed that when you came in. We took this shop over well over 3 years ago now, and we run it as a group of volunteers. So nobody makes money here. I always say this is a not for loss business, because we don't want to lose money, we want to pay the rent, but we do that as a form of, let's say, preservation and for the neighbourhood and for the books and for the love of books. So I think that's a nice bridge to what we're going to have today. I think you all know why you're here. So I really look forward to Ramses and Yvonne having a great conversation about Newton. I did actually read part of your book, Ramses. It's I was inclined to say it's for nerds. Those who are nerds, maybe you should read right now, but that would be unfair because I'm sure it will be very, very interesting. And I love to hear a little bit more about Newton, your famous ancestor as well. So I would say the floor is yours.
Thank you.
Really looking forward to it. Maybe a couple of household things before we actually start. Firstly, it's a big crowd. If we do need to get out of here, there are two ways to get out of here. One is through the shop, but the other one is actually to the side. And the door over there, and then you can exit through the building. I trust that won't be needed, but if it is, please do that in an organized way so nobody gets hurt. Yeah, that's important, I think. Secondly, there will be a break in between where we'll have some tea and coffee if you want, and some snacks or cakes, of course, because it is the King's birthday, so we keep on celebrating. All right, off you go.
Thank you very much. No, thank you everyone for being here. This is really exciting, and I'm really pleased to be able to talk today with Ramses from the Toorn about his book, The Trinity of Mass and Newton's Way, which was published last year. So just a little bit about why we're here. Our meeting is quite a nice story. We met by chance. My family were introduced to Ramses and his father Johan by our common neighbour Melody, and it turns out we live very close by, and all those people are in the audience today. So I'm related to Sir Isaac Newton. I'm a direct descendant of his grandparents, as Isaac Newton didn't have any children himself. As you may well know, Isaac Newton is famous as a 17th century scientist who theorised the laws of gravity. And as the story goes, when Newton was a young man studying at Cambridge University, he, along with his fellow students, were sent home during the plague in the 1660s, which is something I think we can all understand a little bit with the COVID-19 pandemic. It was here he supposedly saw the apple fall from the tree and devised a mathematical explanation for this, gravity. Of course, there's probably a little bit more to this story, but the evidence of his scientific theory remains in his famous book Principia, which is currently kept in the Royal Society Library in London. So in preparation for his book, Ramses studied Principia and what happened before and after its publication in the centuries that followed up until the present day. In Ramses's book, he discusses how the famous criticisms of the Principia in the 18th and 19th century, in his view, show that we somehow actually largely missed the point of it. And he even questions whether such critics actually read the Principia. So Ramses's message is therefore one of awareness and a call for reflection. For example, in Ramses's view, a lot of the arguments in Newton's Principia and their consequences were actually totally overlooked by the physics community, so much so that they became widely associated actually with Einstein, which we will discuss. We will also discuss how it suggests that the Principia apparently was never properly absorbed and understood. Of course, this immediately raises questions of why the Principia was so very influential in the first place, which we will also shine a light on. We will discuss Ramses's book today in two parts, according to the book title. So the first being The Trinity of Mass, looking at the content of Newton's physics, and the second being Newton's Way, which is about him doing physics and how it influenced the history of Western thought and the history of thinking. So without further ado, welcome, Ramses. Thank you for being here.
Yvonne. Thank you, Niels.
Thank you, Niels, as well. So we're going to start with part one, the Trinity of Mass. So Ramses, first of all, you're really passionate about highlighting the fact that some of Newton's findings in Principia became actually associated with Einstein, and question to what extent the Principia was therefore actually read. And I'm curious to know why did you feel the need to highlight this now with your book, and is there like a lack of awareness in the field of physics about it today?
Yeah, thanks. But first of all, let me show you all a copy of the book to see what it looks like. So this is a translation, the first translation in English, 1729, shortly after Sir Isaac died, and the original was in Latin. But it's quite a volume, as you see. So, secondly, before we start talking about the content, let me put it a little bit in historical perspective. So I use this graph of the world population, and it runs from, let's say, the Stone Age at the left and up until the present. And you see an increase in the world population. So in the Stone Age, the world population is counted in millions. This is a logarithmic graph. And then in the Roman age, the world population was about 100 million people. And you see all kinds of events in this graph. So the invention of cities, iron, bronze. You see the Middle Ages with the plague. And then you see at the right hand, about 300 years ago, there's kind of an explosion in world population. And since then, the world population is counted in billions. So it is multiplying in billions. Now in that corner, over here, so this is driven by the Industrial Revolution, steam engines, electricity is invented, and after that came an ICT revolution and the AI revolution in which we are right now. All that is driven by technology, and historians agree that that was enabled by the so-called scientific revolution of the 17th century, which is the subject of the main things that we will talk today. That this book appears here, the Principia is here, that is right in the corner, and that is considered by historians as being kind of a culmination of the scientific revolution. So that kind of puts the book in historical perspective and shows that it's really a kind of a cornerstone in the evolution of the Western civilization. And of course that puts an enormous question, so how can that be? The main content of the book is a theory of gravitation, and that enables astronomers to more accurately calculate the planetary orbits, which had been a goal for about a subject for about 2,000 years. But I think everybody, if you reflect a little bit on this, you cannot explain the growth of population by the fact that we better understand how the planets move. So something else must have happened, and that is one of the things that I want to work towards today as a subject. But first of all, I think this graph shows why it is important in the first place. So why it is a well-spent afternoon of all of you to be here, and together reflect on the content of this book. Now, and then your question was how did I start to think about this? What was the first incentive for me to start studying this book in the first place? And it indeed has to do with notions of mass. I will explain in a minute what these refer to. The background is I was teaching at university to students of aerospace engineering about planetary orbits and the theory that they use to calculate orbits of satellites. And I thought it was nice to explain a little bit about the background of the theory of gravitation and how that came about. So I really wanted to understand what the content, what the meaning of that is, and what the background of it is. And my main message, one of our main messages is that if you really want to understand a concept, it's good to know the arguments behind it, and not just a summary of a result. So that is what I was after. I started looking around in textbooks and I couldn't find it anywhere. And that is why I decided, I need a copy of this, because this is the original, and I wanted to know how did Sir Isaac in the 17th century arrive at his laws of gravitation in the first place. So that was the first incentive for me to study the book.
You have to go back to the source.
Yeah, go back to the source. So that's basically what it is about. That is how I read it now. It was his attempt to deduce the laws of gravitation. Now, if you study books of physics on gravitation these days, in the 20th century textbooks, what you find is they make a distinction between different notions of mass. And I have here a text fragment from a speech by Einstein, and that set the tone for the 20th century. It's hard to see, but let me briefly explain. He uses a few concepts to explain what he was thinking about. So here we have a picture of Einstein. The citation, this text is from 1921. And this picture is about that time, Einstein together with Professor Lorentz in Leiden. So that is what he looked like at the time. But the relevance of this text fragment, which was a speech a lecture that he gave in Princeton University, is he made a distinction between two different kinds of mass. One is gravitational mass, and one is inert mass. Now let me explain what that is. If you get hit, let's say, by a bowling ball, that's serious business. And why is that? Because the thing is massive. So what happens is the bowling ball comes towards you and hits you. And basically you are trying to, you stop the ball from moving. So you change its motion. And that is hard because it is so massive. If you would be hit by, let's say, a balloon of the same size, that would not quite be such a problem. So, a measure for the amount of bowling ball, say, is not its volume, not merely its volume, not only its volume, but it has another property which we call a mass. And in this case, it is a measure for how difficult it is to stop the bowling ball from moving. And that is a 17th century concept that is associated with the name of Galileo, who realized that bodies have a property that is called their inertia, and that is what makes it hard for a body to be stopped, what makes it hard for us to change the motion of an object. That's called inertia. So a property. And the whole notion of property is an interesting one. It goes back to the ancient Greek philosophers who said, well, bodies have properties like color, or like volume, like shape, like whether they are compressible or not, elastic or not. So bodies have all kinds of properties, and how many properties and which properties do bodies actually have? Now this is another one. So there's not only volume, but there's also this inertia. But there might be more properties, because another property of a bowling ball is when you try to lift it from the ground, and immediately you feel it is heavy. And now the question is, and that is one of the key questions for today, is that a different property, or is it somehow the same property? Now, that is something that Einstein brought under the attention, says, well, in principle, I can conceive this as being two distinct properties. I have this inertia, if I push it, it is hard to set it into motion. And I have another property which this is what I feel if I try to lift it, the weight. And those might be two distinct properties, and I call the one inertial mass, the measure for the massivity, and gravitational mass. And then here is an explicit statement by Einstein in 1921 where he says, classical mechanics offers no explanation for this equality, because if you measure the two, the one you can measure by a balance, say, and the other you can measure by measuring how hard it is to accelerate it. If you measure the two quantities, they turn out to be numerically the same, always. Einstein says that is a mystery, and the classical mechanics has no explanation for that. So far good, so good. So Einstein made that statement, and he made it in his writings between 1905 and 1915. Quite sometimes when he was thinking about and trying to explain what he was thinking about while working on general relativity theory. So that was an enormously impressive theory, and that explains probably why all the physics books today and all the sources, if you do internet searches, what I tried it yesterday, if you search for these concepts, what you run into is the name of Einstein all the time, because that is what people think of now when they think about gravitation and mass. Now, what I found when I started reading the Principia for different reasons, once I understood how Newton actually arrived at his theory of gravitation, I learned that he had a very careful, very detailed argument behind it, an explanation of how he arrived at it, and hence what it means and why it is so. And once you understand that there is no room actually for two types of mass. There's only, in the Principia, there's only mass, and if you check the definition, it corresponds to inert mass. So the property that makes a bowling ball hard to stop. And Isaac Newton just deduces that the weight of an object is determined by the same property. So there's only one mass. And that is why I chose as the title for my book the Trinity or mass, because there's actually a third property, but also controlled by the same, and that is, so the whole book is about the motions of the planets around the sun and the motions of the moons around the planets. And what is the explanation for that? Well, the sun pulls at the planets, and that is what keeps them in orbit. And the attraction that the sun exerts on the planet is also proportional to the mass. That is Newton's law of gravitation. Says the attracting power of all bodies in the universe attract one another, and the amount by which they do so is proportional to the mass. And again, he doesn't mention it, he doesn't highlight it, but there's no escape. Once you follow the argumentation, there's no escape. That is also the inertial mass.
Right.
Now, that is of course an astonishing result. When I first realized that that was true and that he had actually deduced that, I thought, how can that be? But this is an astonishing result. How can it be that we attract one another, and the force by which we do that is controlled by my inertia and your inertia, which is a totally different thing. That is how hard it is to set something in motion, but it also controls how strongly masses attract one another.
Sometimes we've also been joking that my family and his family, and then the connection of how we met with Melody is also a trinity of mass and connection in a way, so something in the forces is also working there.
So we have three.
Yeah.
We have inertia, we have weight, and we have attraction.
Yeah.
And that's why the title of the talk and the title of the book is the Trinity.
So just to summarize then, so this later became this idea of not a trinity, but sort of three properties of mass became associated with Einstein. But actually you found in Newton's Principia that there's no place for multiple types or multiple concepts of mass. There are three properties, but only one idea of mass is what you're saying. So then I guess the question becomes then, do we need to criticize Einstein, or how did this sort of happen?
I would never dare to someone like Einstein. I would never dare to.
Make that clear. We would never.
I would never dare to criticize Einstein anyway. But he was struggling. As I said, between 1905 and 1915, he was struggling with general relativity. He tried to explain to his audience, his readers, what he was thinking about. And I believe that Einstein was probably the first to invent these terms to make a distinction. And it was like, it could have been, you can conceive a universe that is different from ours, in which these three properties are controlled by three different phenomena: inertia, weight, and attraction are controlled by three different properties. It might have been so in another universe. And that is what he wanted to put forward, and then say, well, I want physics to explain why in our universe there's only one such property and not three. But what I find alarming is that he put this forward, this idea, with just the intention to explain to his audience what he was thinking about. So it was a didactical choice of terms. And ever since, everybody thinks that before that, or someone like Isaac Newton didn't know or did not have a theory about, or there was just no awareness of that.
And that you say it was
concepts
hidden
could have been. Yeah, there was no, and there is. So I have some arguments that can be found in this book that explain why weight is controlled by the inertial mass. And actually that is exactly the same argument that Einstein put forward. And if you do a search for inertial mass and gravitational mass, this is the argument that you find. And it is really associated with Einstein's name and everything that happened after him. The curious thing is, the very same argument is in the Principia. So, and that I find alarming.
That's why we're
I
here
think
today.
we lost collectively. We lost something there.
Okay.
And how can that be? We can say more about that behind the break. Well, how that came about, I think I have some idea of how that came about. But let me briefly maybe explain the argument.
See, I think so. But if you want to take a break first, we can have the tea break and then come back.
Or maybe we do the physics and then take the break.
Yeah, okay, we'll do that.
I try to make it. So the argument is a well-known one. It is associated with Galileo. You do the search, you see Galileo and the experiments that he might have done by the Tower of Pisa, dropping things. And that is also a remark that you find in the Principia over here. It has been known for a long time, so it's not his own discovery, but he just considers that as something that was well known in the 17th century, observed by others, Galileo from the Tower of Pisa, that if you let heavy bodies drop from equal heights, bodies fall in equal times, no matter what the body is, everything falls at the same rate, in the same way. That's a property. And then the argument is actually quite simple. The reasoning that he had in the Principia is find out why do planets move around the sun and how actually does that work. The first step was that he interpreted the motion of a planet around the sun as falling, like an apple falls from the tree. That is the famous fairy tale.
Story, yes.
He saw an apple fall from the tree and then came to that idea. But nevertheless, so he interpreted the motion of a planet around the sun as falling. So the sun and the planet moves. The moving forward goes without cause. That is the inertial property. If nothing happens, the thing will continue anyway. Like the bowling ball, to stop it from moving, that takes some effort. If nobody takes effort, the thing will just continue. But it doesn't continue in a straight line, it curves towards the sun. And that curvature, that tendency towards the sun, that is interpreted as falling. Now if you say, well, everything falls in the same way, then the next question is, what's the most characteristic property of that gravitational effect in the first place? And that is actually the acceleration itself. If everything at any one point in space, everything will fall at the same pace, it doesn't depend on what the body is. But it is rather a property of the gravitational field of influence itself. So the first property of the gravitational field is the acceleration. And then the force that is associated with that can just be calculated. That is a secondary derived property that can be done by the second law of motion, which was also a well-known thing. In the Principia it is Lex II. That is called Newton's second law of motion, but he didn't claim it. That was another thing that he wrote. Well, that is a well generally known physical law that says if there's an acceleration and you have a body with an inert mass, the force that is needed to induce that acceleration is just a product. You multiply the acceleration by the mass, you get the force. So the acceleration is given. That is the primary property of that point in space. So by means of that law you can calculate what the force is, the gravitational force that acts on the body. But then there's no escape because you use this law of motion, that is the inert mass. And that is the mass that determines the weight. And there we have Einstein's result. There is no gravitational mass.
Right.
You use the same mass, and that was already shown in Principia. Now why is that important? Another reason why it has to be so that all bodies fall the same rate. You see, there is a piece of Latin from the original Latin edition of the Principia. Even if you don't read Latin, you see satellites. Jovian. So these are the moons of Jupiter. That's the problem as we try to understand. You can easily look at Jupiter and its moons by a very simple telescope, like one that you use to look at birds. So if you find Jupiter in the sky, you look at it by a simple telescope, you see its moons. And you can follow those moons. If you follow that for a few weeks, you see the moons of Jupiter move around Jupiter. So that's one thing. But at the same time, Jupiter and its moons together are in orbit around the Sun. And if you study that, you'll see that the fact that the system moves around the Sun does not seem to have any influence on the fact that the moons of Jupiter fall around Jupiter, move around Jupiter. So they fall together around the Sun in the orbit around the Sun. Well, they all fall at the same rate. Otherwise, the falling around the Sun would disturb the motion of the moons around Jupiter. So the fact that all bodies fall in the same way is actually needed to understand what you see if you just look at Jupiter and its moons. And that was a well-known phenomenon at the time. So you see in the Latin text here of the Principia that he is talking about the moons of Jupiter and how they move. So we see again the same argument that everybody thinks that Einstein came up with is emphasized, but it is all over the place in
Wow.
in Principia, really.
Wow.
It's all over the place. Yeah, really.
I see how now you were wondering how much did people actually absorb then what he was writing, or if they even read.
And I think that that is really that was the incentive why I finally wrote this book.
Mm-hmm.
I thought we lost something here.
Yeah. Yeah.
And people should know this. If you, at least if you are teaching the subject, you should know what the background of this classic theory is.
Yeah. No, it's really, really, really interesting. Yeah. Thanks for explaining that. And as you said, we sort of have now only discussed two aspects of mass, but in your book you discussed the third. And if people want to pick up the book, then you can, read about that as well. And I think you said it's better to read it as well because it takes some time to absorb it.
Yeah, so this argument is quite straightforward. I thought I could easily explain it this afternoon. It does not explain why the attraction is also controlled by the same property of mass. But I have found an argument that is in my book, and if anybody is interested, it is a bit more juggling with concepts. But I could explain it on request, let's say, after a second break.
Okay, after a break. Okay, then we'll take a little tea break now, sort of 5-10 minutes-ish, and then we'll come back and continue with Newton's way after the break. Yeah. Oh, it's getting cold now. Mm-hmm. It's getting cold now.
Cold?
Yeah, a little bit.
Get some tea.
Yeah, no worries.
How are we doing?
I think good, yeah. I think this is understandable.